complete. Okay, so we start with, of course, Shannon's measure of information. To remind you, the PJs are the probability, a priori probabilities that of the symbols in which you write the information appearing, showing up. Okay, and that's the classical measure. It's normalized so that I see that I better stand around here. It measures in bits. The units are bits. Now, if we go to the quantum picture, then each symbol is coded in some quantum density operator, and you should remember that there are wave functions and there are mixed states. Now, the measure of information in this level is the von Neumann entropy trace of rho log rho, which we shall use in a moment. And this is, I will normalize from now on in natural information units. That is, the logarithm is the natural log. That's just for convenience. Now, we have an important theorem by Holevo, which is this, which says that the available information, I can interpret it as saying that the available information in a memory, the mutual information between memory and the agent seeking the information is bounded by this expression here. Pi are the probabilities of these particular states here, and S is always a positive functional. Therefore, you can actually bound I by just the von Neumann entropy of this particular weighted sum, which I shall call this state, and that state has, of course, to be normalized to unity. So we have the following, we have formulated the problem in the following way. You have a functional of the density operator. You want a maximum of this S subject to this condition. If you don't say anything else, there is no maximum. You have to say more. For example, if there are some other constraints, then the, I don't know what, I think if I stand here, it'll be better. The I is bounded by the maximum of S rho, where you find the maximum over all rows subject to whatever constraints you have set up. And to be more specific, let me assume that you know the Hamiltonian. You're told what the mean energy of the system is, and of course the normalization. You maximize S of rho under those conditions. This can usually be done. That will give you some bound on the amount of information available in that memory, whatever it be. We know how to calculate this sort of thing because in statistical mechanics we're told that the rho which satisfies these conditions is this canonical one, where Z is the normalization factor, the partition function. Okay, and you find the beta, the parameter beta, the inverse temperature really, by calculating trace rho h, which is the energy of the system. That can be done by this particular formula, setting it to E, which is the number given. And of course, this will give you some particular value of beta, which you insert in the formula, and this will give you the total entropy, which is the bound on the information. This is the way you would do this particular problem here. Now suppose that you're not told the Hamiltonian. You don't know what the Hamiltonian of the system is. You are told maybe the energy of the system. You are told that the system fits inside a particular box. It has some linear dimension, so and so, knowing the internal physics. And this is the direction which I'm taking now. Therefore, let's go to the next slide. And the reason why I begin to talk about black holes is that the easiest answer to this particular question, as I set it up, is which looks like a very hard question to start with, can be given an easy answer using black hole physics, some very simple parts of black hole physics. So I start with a tutorial, 3-slide tutorial of black holes to introduce the important concepts. So we have a black hole, the rotating black hole according to general relativity, which is the Kerr black hole. The Kerr black hole's gravitational field, the observable properties of these black holes are controlled by just two parameters, the mass and the angular momentum. And if you want to know the scale of this black hole, in some coordinates which are very popular, the radius of the border of the black hole, which is called the event horizon, is given by this expression here. G is Newton's constant, c the speed of light. And to get an idea of the dimensions which we're talking about, if the m and j were referring to the sun's angular momentum and mass, then this RH would be about 3 kilometers, and the angular momentum would make a 10% difference in the radius. Now, why is the horizon important? It's because of special relativity, actually. We know from special relativity that signaling velocity in physics must be no more than the speed of light, and this can be described geometrically, drawing the light cone with the slope 1/c, and you say that any signals must travel from this point into the light cone or on the border of the light cone, not outside. That's forbidden. Now, because of the gravitational field in the black hole, the light cones are disposed in such a manner so that you cannot travel outside the black hole, signals cannot go out, because that would be the same thing as traveling over the speed of light. Okay, so this is the reason why the event horizon is a one-way membrane keeping information that has gone into the black hole from leaving, or keeping information from leaving the black hole. That's one thing that one should know. And the other important thing, okay, maybe, okay, seems that the battery is okay, I don't know. Okay, so we have this Kerr black hole, and it's been known since the 1970s that one can ascribe entropy to a black hole in a generic way. Let's remember the Planck length, which is this quantity here, very small length, the only length in physics which does not depend on properties of particles. Now, the black hole entropy is expressed as this formula, the area of the horizon divided by the square of the Planck length, 1/4 of it. That's the black hole entropy. Why is it an entropy? Because it enters the second law in exactly the same way that other entropies enter, and I would like to give you a couple of examples. Let's start with the Schwarzschild black hole, and from now on I only use spherical black holes with no angular momentum. Now, suppose that into this black hole you drop an object, okay, which carries some entropy into the black hole, and of course increase the mass of the black hole. Then it's easy to calculate, at least in various simple examples, that the change in black hole entropy, positive quantity, plus the change in matter entropy, negative quantity, because entropy was lost into the black hole, that always comes out positive. I say there are examples which can be calculated which show this particular second law working. Let's take a second example, a black hole of mass m1, a second black hole of mass m2, which merges with it and produces a somewhat bigger black hole. Okay, there is a theorem by Hawking from about 1970 which says that the change in black hole entropy, actually in areas, but the change in black hole entropy, which is the only kind of entropy here, at the end of the process is bigger than the sum of the black hole entropies before the merger. So you have again the second law working this time only with black hole entropies. Now, I'm going to use this form of the second law to produce one of the, actually two of the entropy bounds that I want to show you. But before that, I need to do two things. One of them is to define black hole temperature. Now, remember that from thermodynamics, the change in entropy of a system that where there is no work is the change in energy divided by the temperature, right? A very elementary formula. Now, we can define black hole entropy by using black hole temperature by using this formula, using mc squared as the energy of the black hole, and I will always refer to mass as energy in accordance with special relativity here. So that's the formula for black hole temperature. Now, if we calculate by replacing the entropy of the black hole by its form in terms of the area of the black hole, and you know that the radius of the black hole is related to its mass, you can actually do this derivative and come out with this formula for the black hole temperature, 1 over the mass. Notice it gets cooler as the black hole is bigger, and the only question is what this temperature really means physically. Now, we have heard from Scott Aronson yesterday or the day before yesterday that a black hole radiates. A black hole formed by collapse will be formed in a radiating state. It radiates Hawking radiation. So there is your black hole. The moment it's formed, it begins radiating. And it's been calculated that the temperature of this radiation is this thing here. So the temperature is the radiation temperature of the black hole, which is the only temperature you could actually ascribe to the black hole, considering that it's such a strange entity. So that's one thing I wanted to get across. And the next thing is the idea of the gravitational redshift. Let's do it this way. Maybe it's better. So gravitational redshift, consider two clocks, accurate clocks, one above the other at a height h, and they're sitting in a gravitational field g. You start with a electromagnetic wave of some frequency f1 according to the first clock, and you let this wave fly up. Okay, when it gets to the second clock, it has a lower frequency f2. The reason is that this, we know that in physics there's always a direct connection between energy and frequency, and since this wave has to fight its way up in the gravitational field, it has to give up energy, which means lower its frequency, so there is a drop in frequency, and the quantitative argument gave Einstein this famous formula for redshift, the change in frequencies as a result of changing place in the gravitational field. This all what happens in flat space, that is when the gravitational fields are very weak. Now what would happen in the field of a black hole? So we take a Schwarzschild black hole, and we look at the metric of the black hole, the description of the gravitational field. Okay, I think I will start using this. So in this metric, this part, the time part, is the important thing for the redshift factor. If you start the wave with frequency f1 at a close point here, or at some point here, when it gets to infinity, it will have this frequency according to this formula, which comes, as I say, from here. Should remember that. And if we consider a point fairly close to the black hole, distance L, physical distance L measured by a meter stick, okay, then this formula can be approximated by a very useful form where you see the distance from the horizon L and divided by a quantity which is essentially twice the radius of the black hole. And this works only when L is small compared to the radius of the black hole. We will use this important formula immediately. So we pass on, and I want to derive now one of the bounds on entropy, which is really a bound on information capacity of a system, in the following way. You start with a Schwarzschild black hole. You take a system which has some radius r in the form of a sphere for simplicity. It has energy, counting all forms of energy, including mass, and it has some entropy S unspecified. From, the reasons are unspecified. You lower this system on a cord until it's almost touching the black hole. Okay, you can get energy out of this process by just winding the cord on the axle of an electric generator and make energy. So we have extracted energy from this body, and the question is how much. You can get a simple formula for this. If you remember the relation between the two frequencies that we had before, you translated this into energies. Now the interpretation is the following. This is the energy in the box, okay? It's carried by the box, or the way it's the proper energy, and this is the energy that is seen from infinity. An observer here judges this object to have this kind of an energy here. That's the formula. Now we do the following simple calculation. The change in the moment that I drop this thing into the black hole, the change in mass energy of the black hole is given by this formula, where I've used this and I've replaced L by the radius of the sphere in accordance with the geometry here. Now you remember the temperature of the horizon. Remember that change in energy divided by temperature is the change in entropy, okay? So you do that calculation and you get this result. Now remember the second law. The second law says that the total change in entropy must be positive. We have a growth in entropy, in black hole entropy, and we have a loss in entropy, S, with a negative sign, right? So when you add these two, it should be a positive result, which immediately tells you that the entropy of the system here must have been bounded in this way, otherwise there will be a violation of the second law. So that's one of the bounds you can get. And the curious thing is that even though I used G and M in all the calculation, the properties of the black hole don't show up in the final formula, so that's a formula independent of the black hole, so long as the black hole was big enough to do comfortably this kind of an experiment. Okay, now there are some caveats with respect to this derivation. First of all, you should remember that the energy in the bound must be the total energy, including mass energy. It's not just the excitation or the thermal energy, but total mass, total energy of the system. Now the bound is restricted to systems with weak self-gravity, systems whose gravitational self-energy is small compared to the total mass or mass energy of the object. So things like you meet in this room or in the kitchen and things like that. Not like a black hole, which has about equal amounts of gravitational and the other kind of energy, okay? So not like black holes or things like that. Now, the reason why you have this restriction, which is an important one, is we use some kind of an perturbation argument to get the bound. Another difficulty is when you have a body which has very strong self-gravity, it's hard to define a radius. I made light of this when I did the description of the experiment, but it's actually difficult to define radius. And there are also, because of this restriction, there are exceptions to this bound, very simple exceptions. For example, matter which has collapsed into a black hole and is already inside will not obey this bound necessarily. It's very easy to show this. Matter outside a black hole will do fine. And it's an interesting curiosity that a full black hole does obey this bound. In fact, the Schwarzschild black hole is exactly at the upper bound, saturates this bound. Kerr black hole is a little below. Black holes obey this universal entropy bound. And the derivation which I gave is somewhat problematic because of a phenomenon called quantum buoyancy. Quantum buoyancy is the following thing. This was put into evidence by Unruh with the Unruh effect. If you suspend a body in the vicinity of a black hole, a body is not moving inertially. It will feel like it's immersed in a bath of thermal radiation, and this radiation buoys the body up in such a way that eventually when the body is sufficiently close to the black hole, it's completely floating. So the way that I described the experiment doesn't really go through exactly because of this flotation, this buoyancy. It changes the energetics, and in fact there is but the thing to remember is that in at least in 3 dimensions, when you do this kind of discussion, the neutral point where the body floats is extremely close to the horizon, so that you can actually ignore the buoyancy in practice. It makes a small correction, not really something to speak about. I will return to this in higher dimensions because it becomes important if I have time. So I've said the caveats, and let's discuss the second entropy bound that you can get from the generalized second law. Okay. These two gentlemen produced what is called the holographic entropy bound, which says the following. If you have a system with some entropy S which happens to fit inside a surface with area A, it doesn't have to be spherical, but some area A, then it is claimed that the entropy of that system is bounded by this quantity, which is basically the entropy of a black hole whose horizon area happens to be the area of this surface, right? And it's written out explicitly here with help of the formula for the Planck length. Now, this is called the holographic bound because it's connected with a set of ideas by a 't Hooft, which is called the holographic principle, which I want to summarize in a kind of caricature by saying that the physics in the interior of a system is determined completely by a theory defined on its boundary. Okay, that's the holographic principle, very much studied today in particle physics, string theory, and so on. And the bound is just a very small article in the holographic principle ideas. Now I want to give you a little proof of the holographic bound. So we take the system, we put it inside the surface of area A, okay, and we allow the system to collapse into a black hole, okay. The second law requires that S, the entropy of the system, was less than the final black hole entropy. Final black hole entropy can be written like this by the formula given before, and since there has been a collapse, the area of the horizon black hole must be smaller than the area of the original surface, and the outer inequality is just the holographic entropy bound. So it's very easy to derive. Now, of course, not every system collapses to a black hole by its own volition, but there are ways that theorists have devised. It's not experimentally viable, but people have devised thought experiments where you can sort of induce any system you want to collapse to a black hole. I wouldn't try to do it in a lab, but I think it's not a fundamental problem there. So you have a proof of the holographic bound. Now I want to compare the two bounds, the universal and holographic bound. So this is entropy, and this is size of the system in centimeters. These are actually natural entropy units. The gray line here is the holographic entropy bound, and you see black holes sitting on it. The Schwarzschild black hole, the holographic bound is actually built on the formula for black hole entropy, so the black hole sits on the, saturates the holographic entropy bound. Now the colored lines are the thing is that the universal entropy bound depends not only on size of the system, but also on the energy. So you have to state different universal bounds depending on the density of the system. So if the density is 10 to the minus 20 grams per centimeter cubed, which is a density of many astronomical systems, they have, you know, for example, a globular cluster of stars, then that would be the bound, and the globular cluster is below it. If you take systems with 1 gram per centimeter cube, all kinds of things around us, that's the bound, and of course all kinds of ordinary things, Coke, bottle, snowflake, Pacific Ocean, and so on, sit below this line. If you take 10 to the 20 grams per centimeter cube, 10 to the 15 actually, that's the density of a neutron star, then that's the bound, and of course the neutron star lies below it. And black holes always lie on the universal bound corresponding to their density. So each black hole has a certain density, sits on the line corresponding to its density. So both holographic and universal bound coincide for black holes. Actually, the black holes saturate both bounds. Okay. Now there is a third bound that I want to introduce. This was discussed first by people like Bill Unruh, Bob Walt, Don Page, and quite a few others. And just to be short, I'll call it the Boltzmann entropy bound because it comes from these two formulae by Boltzmann. The idea, the physical idea of this bound is the following. If you take a piece of hot matter, you know it radiates thermal radiation. So this sort of says that thermal radiation is a very entropic form of matter, if you want, because the matter prefers to produce thermal radiation. And so the idea of the bound is to say that for any system which has a certain volume V and energy E, the entropy of that system is bounded by the entropy of thermal radiation with the same volume and energy. Okay? Let's see what this bound looks like. So we have the two formula by Boltzmann. T is the temperature, V is the volume, and E and S are the energy and entropy of thermal radiation, the very old formula from 150 years ago, something like that. Let's take the volume as spherical, radius r, eliminate temperature between the two formula of Boltzmann, and you get this relation between entropy and energy and radius. If you remember the universal entropy bound as 1 power of this. This has 3/4 power. So this is the formula for black hole radiation. And the Boltzmann entropy bound says that for anything you should have inequality like this. Same formula, right? So that's the Boltzmann entropy bound. You can see that it lies below the universal entropy bound because this quantity to the 3/4 rises slower than the first power. But then you worry what happens if you go the other way to small ER, because then it seems like this will win over the universal entropy bound. I will come back to this issue immediately. For the moment, I want to compare all the three bounds. Here they are, holographic, universal, and Boltzmann. Here are the formulae. I've said them before. There are some exceptions to these various bounds. For example, the holographic bound does not apply to matter which has already collapsed into a black hole. Same for the universal entropy bound. The Boltzmann entropy bound doesn't even apply to a black hole. You can check that a black hole has more entropy than radiation would have with the same volume and energy. And this is an attempt to basically estimate the overshoot of these bounds over the actual entropy of systems. These are systems which I took from the kitchen and the lab and places like these, very simple systems. So the tightest bound is the Boltzmann bound, which can actually get very close to the actual entropy by a few orders of magnitude. Universal entropy bound has a large range, but it can also be close. I will describe one system where it gets very close. And the holographic entropy bound is always a big exaggeration on the actual entropy of ordinary systems. So you can see that this will be more of relevance to actual memories, physical memories. Now, what I want to do now is to try to raise a problem. Okay, suppose that you have a box which is rather thin in one direction, and you fill it with thermal radiation, or photons, okay? Thermal radiation. Now, if this dimension is sufficiently small, the modes which are excited thermally are basically two-dimensional modes, photons that travel this way, not photons that get excited that have a wave vector in this direction, because they cost a lot of energy. So if the temperature is not extremely high, you have only two-dimensional modes. So you can calculate the entropy and the energy of the system by using two-dimensional statistical mechanics, and the energy and entropy go like that in terms of the temperature. A is the area of this surface here, and when you eliminate temperature between these two formula, you get this relation here. It depends on the area, not the volume. Okay, so if you make this very little, very thin, you can actually make the volume go to 0 while the entropy does not go to 0, and you immediately violate the Boltzmann bound that I wrote in the previous transparency. Which means the following, actually, what it means. This is the Riemann zeta, yeah? Wow. Some number that I don't remember. How does it happen? Because of these funny integrals that Boltzmann had, okay? So the Boltzmann entropy bound gets violated by thermal radiation in this case, unless you accept that at every dimension you should have a different entropy, Boltzmann entropy bound. This is essentially a two-dimensional system, so you should have a different Boltzmann entropy bound. So the first question that I have is whether you really have a Boltzmann entropy bound which varies in form from dimension to dimension, from 2, 3, 4 dimensions. Are there different holographic and universal entropy bounds for each dimension, 2 and 3 and 4 dimensions? Finally, do these last two bounds work for radiation systems?
Taking the limit of a very thin system wouldn't mean that quantum confinement dominates over the thermal fluctuations?
over the thermal fluctuations. No, what it means is that photons cannot get excited with wave vector going this way. They're frozen out. Okay.
There's 0-point motion, which is quantum.
Well, that's okay. I mean, the vacuum energy. I will come to that actually very explicitly. But real photons, of course, are excluded. Yeah, you're right. But I will actually go into this. So these are the questions which we want to explore. Why explore higher dimensions? Because of the importance of the problem of higher dimensions in modern particle physics and string theory, which are closely related to these questions of entropy. That's the reason why one should pay attention to them. So let's go and calculate the radiation entropy and the Boltzmann entropy bound in n dimensions. Okay. This is the volume of a sphere of radius r in n dimensions. It's very easy to get, but I won't go into it. Now I calculate the energy of thermal radiation at some temperature T in a box of radius r, big R, spherical box, by using standard statistical mechanics, and I will explain the formula. It goes like the volume, of course, of the box, and then this is the mean energy per photon at temperature beta, which is 1 over T. This is just count the number of phase states, frequency states that you have, and then you integrate over all of them. That's a standard thing, and you can actually do this integral. You see the zeta function of Riemann and the gamma function of Euler. And you can calculate the entropy the same way. This is the expression for entropy of one mode of radiation. Just one word. I'm not taking into account the double spin of the photon, the double helicity. This is just for one helicity. It's just a simple model. And the second integral can also be done. Turns out to be proportional to the energy over the frequency. Okay. Now, what I want to do is to solve this equation for beta, okay? And you get beta in some dimensionless form written like that, where the Cn is the following numerical factor. Excuse me, numerical factor. Okay, now you substitute this expression for beta into this relation for S, and you get the entropy of the radiation in terms of energy and radius. And this is the generalization of the formula that I wrote before for 3 dimensions. So the Boltzmann entropy bound in n dimensions would be just the same formula, right? There would be a bound on S of this form here. And I want to now discuss problems or violations of this bound. So this is the Boltzmann entropy bound in any dimensions. I will show you later numbers, but for the moment, one perceives a problem as follows. This is the relation between entropy and energy that we have for this radiation, thermal radiation in n dimensions. Now, you can immediately see that the S over E can exceed 2 pi r over h bar c by the simple expedient of making beta very big. Beta is 1 over the temperature, so you go to low temperatures, it seems that you violate the universal entropy bound. So radiation violates the universal entropy bound. Is this a true effect or not? Now you start thinking about all the calculation in the last transparency was done using the continuum approximation. There were integrals instead of sums over modes. Okay. Now we know that the continuum approximation is not a very good one at low temperatures, because at low temperatures there are very few states which are excited. That's not a continuum by anybody's opinion. So maybe this is the problem. So we try to avoid the continuum approximation. I'm going to calculate the log of the partition function for a bath of photons, but discretely without any continuum approximation. You have a sum over this kind of expressions. The vacuum, the state with 0 photons will give you a 1 here, right? Energy 0. I'm ignoring the vacuum energy for the moment. The next state, if it does degeneracy G1, will give you this term, and there are of course the continuation. And if you approximate for very large beta, this is the approximation, the first order approximation. Now we calculate the entropy of the system here by the energy you get by the usual derivative comes out to be this to first order. You substitute into the formula for entropy, and you calculate that S over E is beta plus 1 over E1, which does not involve continuum approximation, but you see that if beta is very large, S over E will indeed exceed 2 pi r over h bar c. So you seem to have a violation of the universal entropy bound for a very simple system like thermal radiation. How can this be when we argued that very generally that there is a bound like that? Yes.
So this is at what dimension?
This is what?
At what dimension?
This is for any actually, because yeah, this is really, this would go for, I was very unspecific about the effect of the dimension, so this would go for anything. So what is, but at low temperatures, yeah, I'm working at low temperatures, so what,
so it's for a finite system.
it's a finite system, yeah, all that I say is for finite systems, because there is a size r, and I don't know, from my point of view, infinite systems are not very interesting. Sorry, but they are not very interesting for the subject here. Okay, so where is the problem? Is the bound valid or not valid? Well, we have been forgetting what was mentioned before, the vacuum energy. And just to show you that in a very clear way, let me calculate the ratio S over E in a new way, which is a little more explicit than what I've been showing you up to now. You take the expression for entropy divided by the mean energy of the system, extremize it subject to the condition that rho, the trace of rho, is unity. You know how to do this kind of a problem. Lambda is, of course, the Lagrange multiplier, and you get an expression like that, again, a canonical transformation, a canonical distribution, except that it's a very specific temperature, inverse temperature beta star, and the z is, of course, the partition function, and the beta star happens to be the extreme value of S over E. That is a very strange canonical distribution with a temperature which is defined by the extreme value of S over E. The question is, how do you get that? You combine with the formula for entropy, and you get a very simple formula. Beta star is the zero of the log of z. There's only one zero because this function of beta is monotonically decreasing with beta, so if it has a zero, if the log has a zero, it has only one zero. So there is only one extremum, and this extremum has to be a maximum if it exists. And here is the proof, or some little proof. You differentiate with respect to beta. That's the formula for entropy. And when you differentiate, you can see that there is a cancellation, and you get this expression here. Now, in canonical distribution, which is what that is, energy grows, specific heat is positive, so the energy grows with temperature, so the beta is negative, and you have a negative sign here. The log of z, according to the form here, the log of z goes from positive to negative as you pass this beta star in the direction of growing beta. Okay, so this shows you that this expression here, the derivative, passes from positive to negative as you go through beta star, which means you have a maximum of S over E. So if there is an extremum, it's a maximum, and the question is whether you have an extremum. Now, there is the problem that was bothering us is the following. If you write down the partition function in exact form, the vacuum will contribute 1 here, in this sum here. Then you have more positive terms, and this is supposed to be 1. It doesn't work out. So there is no solution. If this is the description of the spectrum, there is no solution. There is no maximum of S over E. Okay, so we have a problem in the whole setup. And the reason why we have a problem is we forgot about Casimir or vacuum energy, which is the following phenomenon for those of you who haven't heard it. Suppose you take as an example a sphere. This will be in 3 dimensions for the example. It's radius r, spherical cavity, and you calculate the energy of the vacuum state, the no photon state of the electromagnetic field inside this cavity. This was done back in the, I think in the 70s or 80s already by Boyer and later by Schwinger and company. and you get a vacuum energy which is non-zero depending on the radius of the sphere. So the ground energy of this system, the electromagnetic field, is actually bigger than this, at least that quantity here. We didn't take this into account. There are more examples which bring out some other feature which has to be dealt with. Suppose you have a cube size A. You have a cube of size A. I have about, how much? 5 minutes. Okay, I'll try to speed up. Okay, suppose you take a scalar field in 3 dimensions in a cube like that, then this is the vacuum energy. It comes out negative, and the same thing would be true in 5 dimensions. I have managed to get these numbers from the literature. So the question, what do you do with negative energy? You should remember that there are these walls which have to confine the electromagnetic field. Now, if the walls had no rigidity, then this cube would simply collapse because it wants to make its energy as small as possible. So they must be rigid in some sense, and by special relativity you can show that this gives the walls a certain mass which exceeds this amount by a factor of a few. So in fact the total energy of this system, the lowest one, is a few times this factor but positive. So in fact you have a situation something like this. Doesn't matter what the vacuum energy is, the minimum energy of the system, the ground energy, would be positive. Okay, so let's fix the discussion that we had as follows. Every energy of the system, you subtract out the ground energy and you have the energy of excitation above it. Then this would be the true, this is the true partition function. This is the partition function not ignoring vacuum energy, ignoring ground energy, so you have separated the factor there. And then the formula for the beta star would be changed to something like this. Okay, so let's calculate log of z. Again, I do it by continuum approximation because that apparently was not the source of the problem. And you can do an integration by parts, and you recognize that this part of the log of z is the energy above the ground state that we computed before. So that number is actually already known. Okay, so if I substitute this expression for log z into here, I get this formula or this equation for beta star, which has very clear physical meaning. And now I know that the energy above ground state has been calculated before, and it's something like this. Okay, so I put it into the first formula of the line, and actually what I did, I substituted this in here and I solved for beta. Okay, beta comes out to be that with a numerical coefficient like this, and this I can put back into the expression for S over E being beta star, gives me an expression for the maximum value of S over E, which I can now try to evaluate. Now, this is a little table for this numerical coefficient here for various dimensions running up to infinity, and you can see that it doesn't vary that much. It's a little under unity, so this is a little bit under unity. What about this ratio here, hc over r divided by the ground energy? For the example of the sphere with electromagnetic field inside, this was about 20 in the actual calculation. So let's take 20. We have to take a fourth root because this was in 3 dimensions. So this number comes out to be 1.77. Okay, so the entropy over energy and the maximum is 1.77 R over H bar C. The bound, universal entropy bound, tells you something like this, so it's consistent. And you can go through examples, a few examples, those where one can calculate the vacuum energies, and you find out that there is perfect consistency if you remember the 0-point energy of the electromagnetic field. Okay. I wanted to discuss, but I don't have that much time, so I will sort of show. This is a proof by Busso, very recent actually, of the fact that the universal entropy bound looks exactly the same in n dimensions as it does in 3. The idea was to take a black hole in n dimensions. That's the metric. Okay, in the metric you have this metric coefficient. This is the metric of n minus 1 sphere. Okay, that's the metric coefficient B that appears here. The RH is the radius of the horizon. There appears here the gravitational constant in n dimensions, and I will try to explain why in n dimensions it's different than in 3 dimensions. That's the again the area of n minus 1 sphere. What you do is to consider a little object which carries some energy, radius, and has entropy at some distance, coordinate distance delta r from the horizon of the black hole. You calculate what physical distance this amounts to in some approximation, and then you drop the system into the black hole. You calculate how much the mass has increased. You need to multiply the energy of the object by the redshift factor square root of that at the point where the object was sitting, and you can actually do the calculation and convert it into an expression that contains the physical distance at which you drop the system. And this physical distance cannot be smaller than r, the radius of the sphere. So now you calculate you write the black hole entropy for n dimensions. The only difference is that the G must be for n dimensions, and you calculate how much this black hole entropy changes upon the absorption of the sphere, and you find this result here. Very simple algebra. Now delta L, as I said, can be made down, can be brought down to R, and then if you demand that the second law work, then this is the upper bound on the entropy of the system, and it looks exactly the same in any number of dimensions. Do I have any time left? 1 minute? Yeah, 1 minute. Good. Then I want to compare the 2 bounds. Let me go up to here. This is the holographic entropy bound in n dimensions, just the usual one with G depending on the number of dimensions. I have explained that, and this is the universal bound correct in any number of dimensions. Now I want to explain why G of n depends in its units on the number of dimensions. The dimensions of G depend on the number of dimensions. It's kind of a complicated sentence. Why is this important? Because if it depends on the number of dimensions, then the number of Gn depends on the number of dimensions. So what number are you going to use in comparing these two? So there is a slight problem. This is the reason why Gn depends on the number of dimensions. If Newton wrote his law for acceleration due to gravity in n dimensions, he would have written something like this. The reason, of course, G must depend on n, presumably, and this 1 over r to the n minus 1 is the derivative of the solution of Laplace's equation in n dimensions. So that's the generalization of the 1 over r squared law. If you make an analysis, dimensional analysis of this expression here, you can get the dimensions of Gn, which are kind of funny. And with these dimensions, you can actually understand why one writes the radius of the horizon in this funny way. Anyway, here is the punchline. Take an object of radius r, some mass. So this is the radius of the black hole, which has that mass, and therefore eta must be some number bigger than 1 for an ordinary object. In terms of this definition, you can show that the ratio of the 2 bounds is this dimensionless number. Let's analyze it in the following way. If eta equal to 1, that is, if you deal with a black hole, this factor is of course 2, and in 3 dimensions this is also 2, so the ratio is 1, the 2 bounds agree. If you go to higher dimensions, you calculate that you find that the holographic entropy bound is below the universal entropy bound, which made Busso remark that maybe this says that you should be able to optimize the universal entropy bound, make it smaller, because there is some leeway up to the black hole limit. This is not true really, and the reason is the following. Eta cannot be arbitrarily close to 1. In 3 dimensions, we know that a body which has gravity will collapse to a black hole unless it's a factor of a few larger than the horizon of the black hole with the same mass, a factor of 2 or 3. So let's just assume uniformly for all dimensions that eta is 1.05, just a little bit more than 1. you immediately find that the universal entropy bound is below the holographic entropy bound. It's actually the more efficient bound, and the problem goes away. So the ranking of the three bounds is the Boltzmann entropy bound, when it works, is the most efficient. Then the universal entropy bound more lax, and the holographic entropy bound extremely lax. And the challenge, and then now I'm summarizing, the challenge in this field is to find entropy bounds which are not lax, that is very stringent, but apparently it's very easy to get bounds which don't work for all cases, and we do want generic bounds to try to address the problem of the memory with the maximum amount of information. So that's where the subject stands. I'm okay with time? Yes, okay.
Okay, so let's thank you. Yes. We have time for a few short questions.
So the Boltzmann entropy bound, you talked about one situation where it can be violated, where the system is confined to a lower number of spatial dimensions. Is it known that that's the only way it can be violated, or are there other?
No, there are other ways. I said any black hole violates the Boltzmann entropy bound. I figure that there are other ways. But it's a pretty general bound if you pay attention to write it in a different way in every dimension, right? I mean, it has a different form. It's not uniform.
Just a really stupid question. How does ER to the 2/3 power violate a bound involving ER to the 3/4 power? Is it that ER is very small?
How ER to the 2/3 you're talking in two dimensions.
Yeah, right.
In two dimensions, how does it violate? No, the reason is that the area appears here, and the area doesn't change when you let the volume go to 0. Okay, so you beat the other bound.
Questions or comments?
So can you comment on how much information, and if these bounds are, take one of them, how much information does a cubic centimeter hold?
First of all, the important thing is not volume, because if we use the Boltzmann entropy bound, it's some fractional power of volume. That is the bound. In terms of numbers, they're pretty high bounds, okay? But the important thing is if you compare ordinary systems with these bounds, you find that the Boltzmann entropy bound can be approached. In the case of the universal entropy bound, if you use radiation and you take into account the vacuum energy to get consistency, you can get also very close to the bound. That is a system of thermal radiation, and you take into account the vacuum energy, can get close to the universal entropy bound by a factor of a few. Numbers you want, like bits, when you get close, it's not many bits. It's the S over E, which is the factor of merit, yeah, the number of merit. But it's very easy to calculate the numbers of bits. You can do it yourself.
For the holographic bound, it goes 10 to the 60.
Yeah, it's very
bits per
large.
square meter.
Right. Yeah.
10 to the 69 bits per square meter.
66, I would say.
Oh, really?
But this 10 to the minus 33 is the Planck length, so square of
I
that.
was doing
Well, it doesn't matter.
meters.
What are three orders of
I
magnitude?
remember this from Busse's survey article. It was
Okay.
like,
It doesn't matter right now.
So that's a very lenient bound.
yes.
Yeah.
Okay, so on that note, if we can store all that information in square meter, so
Yeah.
I think that's thank the speaker.
Okay. Thank you.
So next,
I-
Okay.